Hello students, welcome to Talk on Civil Engineering. Let us discuss one more problem from stresses chapter in pre-stressed concrete beam. So here is asking to calculate the stresses, the extreme stresses in the pre-stressed concrete member using load balancing concept and stress concept. Okay, so he has given all the required data. Firstly, let us calculate the stresses using stress concept. Then later we'll see the load balancing concept. Okay, extreme stresses using stress concept. Okay, so we all know in stress concept we'll be having the direct stress due to pre-stressing force plus the stress due to eccentricity of tendon and plus due to the external load. Okay, so firstly let us calculate what is a direct stress due to pre-stressing force. So the formula we are going to use is pre-stressing force divided by area of concrete. Okay, so here in the question he has given the pre-stressing force of 1200 kilonewtons, and remember always this direct stress will be positive. Okay, so it is 1200 kilonewtons. I'm converting in newtons, and area of concrete, so it is 400 by 600. So here area of concrete is equal to 400 into 600. So 6 4 is 24. So it is 240 into 10 to the power of 3 mm square. Okay, so area of concrete is 240 into 10 to the power of 3 mm square. So if you calculate this, we'll get the stress, the direct stress of plus 5 Newton per mm square. Okay, and now let us calculate what is the stress due to the eccentricity of the tendon. Stress due to eccentricity of tendon. Okay, so for this, the formula is minus or plus PE by section modulus. Okay, minus because above the neutral axis due to this due to the tendon profile, we'll get the minus on above the neutral axis, plus on plus below the neutral axis. So here this tendon is a parabolic tendon. So here it is a parabolic tendon. So the tendon is something like this, right? So due to this tendon profile, your beam bends like this. It has a hogging bending. So it will have hogging bending. So above it will be tension and below it will be compression plus. So that's the reason due to this tendon profile you will have minus and plus. Okay, minus above in above fibers, plus in below fibers. Okay, so let us substitute. So P is 1200 into 10 to the power of 3. And what is the eccentricity? So eccentricity is 100. Okay, so eccentricity E is 100 divided by Z value we need to calculate. So Z is equal to BD square by 6, right? So B is 400, D is 600 square by 6. So it will be, so the Z value will be 240 into 10 to the power of 5 mm cube. Okay, so let us substitute this value. It is 240 into 10 to the power of 5. Okay, so if you calculate this, we'll get the value around minus or plus 5 Newton per mm square. Okay, now let us calculate the stress due to the external load. So here I'm assuming the load which is given like here he has given 40 kilonewton per meter. I'm assuming this is the load including the self weight. Okay, so stress due to the external load. So before we know the formula, that is, so here the symbol will be plus or minus, right? So plus or minus moment due to the load divided by Z. Okay, so we need to calculate what is the moment here. So moment due to the load is equal to WL square by 8 because it is a UDL. So it will be WL square by 8. So W as given as 40. L is 6 meters. L is 6 meters by 8. So it will be 180 kilonewton meter. Okay. So let us substitute the value, plus or minus 180 into 10 to the power of 6 in Newton meter, Newton mm. And Z value is 240 into 10 to the power of 5. Okay. So if you calculate this, we'll get the value around plus or minus 7.5 Newton per mm square, 6 mm square. Okay. So I hope you know why I have given plus or minus, because due to the load, the beam tends to bend in a sagging shape, right? So it will have a sagging bending. Due to the external load, it will bend like this. So in this case, above the neutral axis it will be positive, and below the neutral axis it will be negative. So this is due to the external load, only due to the external load. Okay. So now we got all the stresses. Now for these stresses, let us draw the stress distribution diagram. So this is a beam. Here we have beam and the tender. Draw the top line and bottom line, top fiber and bottom fiber, at the center line as well. Okay. So firstly, we are having the direct stress of 5 Newton per mm square, which is positive from top to bottom. So this is positive. So this is plus 5 Newton per mm square. Plus, then we have the stress due to eccentricity, which is minus and plus 5 Newton per mm square, right? So minus on top and plus on bottom. So this is plus 5 Newton per mm square, and this is minus 5 Newton per mm square. Okay. Plus, now we have stress due to the external load, so which is plus or minus 7.5. So plus on top plus 7.5 Newton per mm square, and at bottom it is minus 7.5 Newton per mm square. Okay. Now the resultant will be on top. So here on top it will be 7 plus 7.5. So resultant in the sense the summation of top and the bottom. Okay. So the summation of top stresses, so it will be plus 7.5 Newton per mm square, and at the bottom, so this is also plus 5 Newton per mm square, right? So it will be 5 plus 5, it is 10. 10 minus 7.5. It will be plus 2.5. So 10 minus 7.5 will be 2.5. So everything in plus, positive. That means compression. Okay. So this is how we can calculate the stresses using the stress concept. We all know this concept very well, right? Now let us calculate the stresses using load balancing. Load balancing concept. Okay. So here we'll be focusing on balancing the load. Okay. So here on top of the beam, try to understand this concept. So this is a beam. Your tendon is located in a parabolic profile, something like this. Okay. So which is having a eccentricity of 100. Okay. And we have external load of 40 kilonewtons per meter. Okay. So this external load will be balanced by the tendon profile, which is provided in a parabolic manner, right? So with the tendon, which is carrying a pre-stressing force of 1200 kilonewton, 1200 kilonewton will try to counteract this load of 40 kilonewton meter. So it will try to counteract this 40 kilonewton meter. Okay, so it will act like this. So there will be a upward thrust counteracting the 40 kilonewton per meter, that external load. Okay, so this is called upward thrust. Okay, so these two, the 40 kilonewton will be counteracted by the upward thrust, and whatever the load left, that is a net load. So for that load, we will be calculating the stress. Okay, and one more thing here. So here the direct stress will be common. So the direct stress will be there only due to this tendon profile. The tendon profile in the sense the tendon is eccentrically provided, right? So due to the eccentricity of the tendon, so you will have the upward thrust counteracting this 40 kilonewton meter. Okay. So after the counteracting, whatever the load that is left, so for that we'll be calculating the stresses. Okay. Now let us calculate the upward thrust first. Okay. So if you see here, this upward thrust is counteracting the 40 kilonewton, and this is eccentrically provided, right? So we know due to the eccentricity, what is the moment? So the moment due to the eccentricity of the tendon. So it is P into E. Okay. So P, the force into the eccentricity of the tendon. Okay. And so let it be the equation 1, moment 1. And for moment 2, due to the external load, what is the formula? So that is load into L square by 8. Okay. So let it be upward load, upward thrust. Okay. So let this equation be 2. Okay. Now let us equate equation 1 and equation 2. Equate equation 1 and 2. Okay. So it is PE equal to upward thrust to L square by 8. Okay. So we need to find out what is this upward thrust. Okay. Let us find out that one. So send 8 and L square to that side. So it will be upward thrust is equal to 8 PE divided by L square. Okay. So now we have all these values. We can directly substitute. So 8 and P value, that place resting force is 1200 kilonewtons. And so this is I'm substituting in kilonewton per meter in kilonewtons and meters itself. Okay. So E, it is 0.1. So because I am substituting in meters, and L, so it is 6 meters. So it will be 6 squared. Okay. So now if you calculate this, we'll get value around 26.67 kilonewton per meter. So this is the upward thrust. So that is 26.67 kilonewton per meter. Okay. So the tendon, the eccentric tendon, the parabolic eccentric tendon is counteracting up to 26.67 kilonewtons of 40 kilonewton meter. So there will be some net load will be there, right? So now let us find out what is that net downward load. Net downward load is equal to, let it be Wn. So Wn will be equal to 40. So that is the external load minus the upward thrust. So that is 26.67. Okay. So it will be, the net load will be 13.33 kilonewton per meter. Okay. So if we calculate the stress only due to this net downward load, that will be enough. Okay. Because the other load is already compensated, that is counteracted. Okay. So that is subtracted. So now we can calculate on stress due to only this net downward load, that is 13.33 kilonewton. Okay. Now let us calculate the stresses. So first one, the stress due to free stress. So that is the direct stress. So the direct stress will be common. Okay. So that is plus P by area of concrete, right? So it is 1200 into 10 to the power of 3, and area of concrete is 240 into 10 to the power of 3. Okay. So it will be plus 5 Newton per mm square. Okay. Now let us calculate the stress due to the net load. Stress due to the net downward load. Okay. So what is the formula? It is plus or minus moment due to net downward load divided by section modulus. So for this, we need to calculate what is the moment due to this net downward load. So that is WNL square by 8. So what is the WN net load? So that is 13.33, right? So 13.33 into 6 square divided by 8. Okay. So the net downward load moment will be 59.98 kilonewton meter. Okay. So now let us calculate the stress plus or minus. Moment we got as 59.98 into 10 to the power of 6, and section modulus we have already calculated, that is 240 into 10 to the power of 5. Right. So if you calculate this value will be around plus or minus 2.5 Newton per mm square. Okay. Now let us draw the stress distribution diagram. The beam tendon at the center. So we need to draw the top line, the bottom line for the reference on the center. Okay. So the direct stress, which is positive, 5 Newton per mm square on top, 5 Newton per mm square throughout the session, which is positive, and plus the stress due to this net downward load, which is positive on top, that is plus 2.5 Newton per mm square, and minus 2.5 Newton per mm square on bottom. Now find the resultant stress by adding top stresses and bottom stresses. So on top, it will be 5 plus 2.5, it will be 7.5 plus 7.5 Newton per mm square. And bottom, 5 minus 2.5 will be plus 2.5 Newton per mm square. So everything in plus. Okay. So using the load balancing concept, we got on top extreme in top extreme fiber we got stress as 7.5. In bottom extreme fiber we got stress as plus 2.5. And using the stress concept as well, stress concept also we got the same value on top 7.5, at bottom 2.5. Okay. So this is how we are going to calculate. Okay. Thank you.